This video is for Calculus BC, sections 9, 9, and 9, 10. We're going to start with number 5. We've already done numbers 1, 2, 3, and 4 in class. Okay, so number 5 asks us to write the first 4 terms and the general term for the power series e to the negative x squared. So what we're going to do is we're going to use a known series to help us do this. So the series that we should already know is this one. We should remember that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus plus x to the n over n factorial. So we're presupposing that we remember this, and this is what we're going to base our new series on. So we're going to try to write a power series for f of x equals e to the negative x squared. And I'm going to do that by plugging in a negative x squared wherever I see an x. So this series that I'm about to write will be my new series. Here we go. It's going to be e to the negative x squared is equal to 1 plus negative x squared plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial plus plus negative x squared to the n over n factorial. So using substitution again, we've used that quite a bit. I've just replaced all of my x's with negative x squared. And so I'm going to clean this series up just a little bit. Here's what it would look like. E to the negative x squared is equal to 1 minus x squared plus, because of course a negative squared gives us a positive, so it would be plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus plus we could say negative 1 to the n x to the 2n over n factorial. I'm just using my typical exponent rules to do this. So if you want, we could perhaps talk about this later. The interval of convergence for this, if you use the ratio test, you're going to find that it's negative infinity to infinity. Okay, let's take a look at the next part to this. This next part is perhaps the most interesting part. This is one of the motivators, one of the reasons that we actually study power series is to do something like this next part. So let's check that out. Okay, so I've rewritten the series that we just found in the previous question. It says use the first 4 terms of the power series that we just found to approximate the integral from 0 to 1 of e to the negative x squared. So if you think about this integral that they're asking us to do, we don't have an antiderivative for e to the negative x squared. If you stop and think about that, it's clearly a composite, but there's no derivative of the inside as part of the integrand, and it's not a fraction that we're used to seeing. It's not a partial fraction or a maybe an arctan or arcsine or ln or whatever. It's nothing like that, and so we really don't have a nice antiderivative form for this. So what we're going to do is we're going to say that because we know that this e to the negative x squared is equal to this series over here, I could really just replace e to the negative x squared with that series. But I can't, of course, do an infinite number of terms. This just says use the first 4 terms. That's what I'm going to do. So it's going to be integral from 0 to 1 of 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial dx. So this is a polynomial. So this is actually pretty easy for us to find the antiderivative. So let's give it a shot. So this would equal x minus 1/3 x cubed plus x to the 5th over 10 minus x to the 7th over 42. We're going to be evaluating that from 0 to 1. Obviously, it's very easy to work with polynomials compared to things like e to the negative x squared. And thankfully, we just have a 0 and a 1 here. So I'm going to plug in a 1. That's going to give me 1 minus 1/3 plus 1/10 minus 1 over 42. And when you plug in a 0, you just get 0. So let's see here. If we just add a few fractions together, we'll actually have an answer here. Let's see here. Oh boy. Common denominator, I don't know. I'll think about it here. So I'm coming up with the lowest common denominator of 210. So let's see here. That would be 210 over 210 minus 70 over 210 plus 30 over 210 minus 5 over 210. And that would give us, 140, 170. I'm coming up with 165 over 210. Okay, I'm sure we could use Math 9 to see that that's pretty close, but I'm feeling pretty confident with that. Notice there is one other part to this. It does say calculate the maximum error for this approximation. So let's notice this series that we got, the series down here. Really important feature of it is that this is an alternating series. So with an alternating series, the error is always less than or equal to the first neglected term. So we used all 4 terms, so we're probably going to have to come up with another term for this, but I think we can probably do that. So here's what I'm going to say for my error. I'm going to say integral from 0 to 1 of e to the negative x squared dx minus my approximation, which was 165 over 210, is less than or equal to that first neglected term. I can do that because we have a converging alternating series. So my first neglected term, let's see here, let me just, I'll just squeeze one in back up here at the top. It would be plus x to the 8th over 4 factorial. That would be that next term. And I just need to plug in a 1 to get the term in the series that came next there. So it'd be, let's see here, we'd have, if I plug in right here, we're missing that term, so it'd be x to the 9th over 9 times 4 factorial. So it'd be 9 times 24, so I think that's 216. Okay, so plugging in a 1 then, it would have gone right in here, gives me 1 over 216. So that tells me that my error is less than or equal to the first neglected term. That would be 1 over 216. That's my maximum error. So what I'm using there is the alternating series error bound. Good review from several sections ago. Okay, let's move on to number 6. Number 6 says write the first 4 terms and the general term for the of the power series. F of x is equal to x over 1 minus x. Okay, so once again, we're going to try to use a known series to try to help us find a new series. So take a moment and think about which of our 4 known series you would try to use to try to manipulate into becoming this new series that we want. So for number 6, I hope that you're thinking about using 1 over 1 minus x. The reason why I think we should use 1 over 1 minus x to help us is because the function that we're trying to approximate is very, very similar to that series, or to that expression. 1 over 1 minus x, x over 1 minus x. So let's start off by practicing writing 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus dot 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 plus x to the n. So please take a minute and think about this. What do we need to do as far as the manipulation goes? So far we've really just used substitution. Is substitution going to be the thing that gets it done for us here? And the truth is this time substitution is not what we want to use. I just noticed that, in my known series, the numerator is 1. In my target series, the numerator is x. The way that I get a numerator to change from 1 to an x would be to multiply by x. So that's what I'm going to do. I'm going to multiply the left side by x. That gives me x over 1 minus x. That's what I'm wanting. And then my series, I just multiply an x times each of the terms. So 1 times x gives me x. X times x gives me plus x squared. And so on and so forth, plus x cubed, plus x to the 4th, plus dot dot dot, plus x times x to the n. And if we wanted to clean that up, that nth term, certainly can do that. It would be plus dot 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 plus x to the n plus 1. We add our exponents when we multiply our bases. You fix that there a little bit. Okay, so there is our first 4 terms and our nth term. And then as far as an interval of convergence goes, I think we're going to find something that maybe we would expect. I'm going to use my nth term. My nth term is really x to the n plus 1. So I set up my ratio test. Limit is n goes to infinity, and it would be x to the n plus 1 plus 1, so that would be n plus 2, over x to the n plus 1. I want that to be less than 1. So when I do my cancellations here, I get limit as n goes to infinity of absolute value of x is less than 1. So my interval of convergence then would be -1 is less than x, which is less than 1. And you're going to find that when you test both endpoints, you get nth term test divergence, and so neither endpoint would be included, and so that would be your interval of convergence. All right, let's take a minute and look at number 7. All right, so for number 7, you're going to find is kind of a combination of strategies. We are asked to find the first 4 terms and the general term for a power series for this function right here. So once again, we are going to try to use a known series to help us write the terms for a new series. So again, take a minute and think about what you might use to help us approximate, to help us write a series for this function. And I'm hoping that as you think about that, you're coming up with this again. The geometric series is what most closely resembles this. It's starting to get pretty manipulated, but it's a fraction. The other things we have to work with are cosine, sine, and e to the x, none of which look like that at all. And so we really have to start with this. I think you're going to find some cool things that happen with this one. So just as a reminder, 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus dot 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 plus x to the n. If we have an infinite number of terms on our interval of convergence, those the series here, the power series, will converge to 1 over 1 minus x. So the first thing that I notice here is instead of 1 over 1 minus x, we have something over 1 minus x squared. That x squared being, there we go, that x squared being kind of a key feature there. And so I think that I can handle that. I think that I can, messed that up. Let me start over again. Sorry about that. Let me just scratch this out real quick. 1 plus x squared plus x cubed. Okay, and now we're back. Sorry about that. I pushed the wrong button. So, 1 over 1 minus x squared. That's kind of where I want to go with this. I'll handle the top in just a minute. But if I want that to be 1 minus x squared at the bottom, what I'm going to do is I'm going to replace my x with just x squared. So I'm going to write this. We're going to do this in a couple of stages. So I'm going to write it like this. This is getting us a little bit closer. So I'm just going to replace all of my x's with x squareds. Here's what that would look like. 1 plus x squared plus x squared squared, that would be x to the 4th, plus x squared cubed, that would be x to the 6th, plus dot 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 plus x squared to the n. That would just be x to the 2n. Okay, and then what is it exactly that we do with that numerator? The numerator being 1 plus x. Well, again, I look at my original numerator in my known series, and it's just a 1. So you might be tempted to say, just go plus x. That's some pretty bad math, though, if you think about how that works with fractions. We'd need a common denominator to actually add that. So I don't think adding an x to the numerator is going to be what we want to do here. We've got to think about what we would do to both sides of this equation to make it work. And the answer is, what we would want to do is we would want to multiply both sides by 1 plus x. It's going to be a multiplication here. So if I multiply 1 plus x through this whole thing, I'm going to have what I need. So multiplying by the fraction, I just get 1 plus x over 1 minus x squared. And then when I multiply into the series, it's going to be a little more complicated. I'm just going to distribute. So that would be 1 plus x for my first term. And then when I distribute to the second term, it would be plus x squared parentheses 1 plus x. And just kind of keep going here. So it would be plus x to the 4th parentheses 1 plus x. And then plus x to the 6th parentheses 1 plus x. And then finally here it'd be plus dot 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 plus it'd be x to the 2n times 1 plus x. There we go. Okay, so let's do a little cleanup work here, and I think we'll find a pretty interesting result. So as I clean this up, I end up with 1 plus x plus, when I distribute the x squared, I end up with x squared plus x cubed. When I distribute this, I end up with x to the 4th plus x to the 5th. See an interesting pattern, right? So distributing finally, we get x to the 6th plus x to the 7th. Oops, that's supposed to be a 7. Plus dot 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 plus it would be x to the 2n plus x to the 2n plus 1. Interesting. What does this look like? Of course, it looks like just the regular geometric series, right? I mean, interesting that these would look the same, but I just want to remind you of something. We could have, obviously I chose not to, but we could have done kind of a preemptive manipulation at the very start. If you think back to the very beginning, 1 plus x over 1 minus x squared, if you think back to some algebra stuff from the past, couldn't we have factored the denominator? I think we could have. We could have written f of x is equal to 1 plus x over, the denominator is just the difference of squares. So that would be 1 minus x times 1 plus x. And then, of course, the 1 plus x's would have canceled out, leaving us with 1 over 1 minus x. So this really was the geometric series just in disguise. But I think it was worthwhile doing the manipulations, kind of come back around full circle to see that that's all this really was. But it was just in disguised form. Let's go ahead and take a look at number 8. Okay, so for number 8, very familiar start to the question. I think after number 8, things change a little bit. So it says, write the first 4 terms and the general term of the power series for x over 3 plus x. So once again, we want to try to figure out a known series that would help us with this, that would help us arrive at a series for x over 3 plus x. And the way that we're going to do that, the series we're going to use, is 1 over 1 minus x. The reason why we're using that is that's the only one that remotely looks like what we have here. The other ones we have are sine, cosine, and e to the x. This does not look like that. So let's use 1 over 1 minus x. So it would be 1 plus x squared plus x cubed plus dot 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 plus x to the n. And like the previous one, we're going to have to do this in stages. We're going to do our substitution first. And so I noticed that my denominators are pretty different looking. 3 plus x, and then of course this one over here is 1 minus x. We need to take a minute and really kind of think about what the x would have to be. We're going to have to use substitution here. What is the x going to have to be to make 1 over 1 minus x end up being something over 3 plus x? So take a minute and think that one over. Feel free to pause the video, try it, figure it out, and then start the video up again if you want. Okay, so here's what we do. We're going to do this in a couple stages. It's going to be 1 over 1 minus. In place of the x, we need to put negative 2 minus x. If you think about what's going to happen there, it's going to really be 1 plus 2. That gives us a 3. And then that minus would get distributed there, and we get plus x. So what that means then is I need to replace all my x's with negative 2 minus x. So that'll be 1 plus negative 2 minus x plus negative 2 minus x squared plus negative 2 minus x to the third plus dot 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 plus negative 2 minus x to the n. And then my final step here is to figure out a way to make my numerator change from a 1 to an x. And again, stop and think about that if you want. Pause the video if needed. But the bottom line is, what we're going to have to do is multiply both sides by x. So if I multiply the left side by x, I'm going to get x over 3 plus x. That was my goal. Multiply the right side by x, I get x plus x times negative 2 minus x plus x times negative 2 minus x squared, so on and so forth. Oops. There we go. Negative 2 minus x to the third. I guess I can fit this in. Plus dot 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 plus x times negative 2 minus x all to the nth. Notice we did have to move our centering point. Our original centering point is 0. I just moved it over to negative 2. So I guess just a note there on that one. Let's take a look at a few more. Let's look at number 9. Okay, so for number 9, it says use the Maclaurin series for sine of x to evaluate that particular limit. So let's give it a shot. Limit as x goes to 0 of, in place of sine of x, I'm going to put that Maclaurin series for sine. So that would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus, I'll just put dot dot dot, and I think you'll kind of see where this is going here in a minute. And then we have minus x over x to the 3rd. So I'm sure you can notice here that the x's in the top are going to add out. So that leaves me with limit as x goes to 0 of negative x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot 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 all over x cubed. So I think at this point what I'm going to do is divide the x cubed out of everything. So that'll give me the limit as x goes to 0. And when I cancel the x cubed out of the first term, I just get negative 1 over 3 factorial. When I do the same thing to the next term, I get x squared over 5 factorial plus, I guess technically it'd be a minus, wouldn't it? If I did another term here, it'd be minus x to the 4th over 7 factorial. I'll just put plus dot dot dot. So now I think we can evaluate this limit fairly easily. As I try to evaluate as x goes to 0, I feel pretty confident that this term will go to 0, that term will go to 0, and then all the rest of the terms will go to 0 as well. I am left with that first term of negative 1 over 3 factorial, which of course is negative 1/6. Okay, let's move on to numbers 10 and 11. Okay, so with 10 and 11, question's pretty different. It says use a known series to determine the function represented by that series. And so this is really kind of backwards from what we've been doing. We're looking at a series that has been manipulated, and we're supposed to go backwards and figure out the function that is represented here. So this takes, I think this takes a great deal of energy and thought. You obviously have to be very, very good at remembering the 4 known series. Any question like this will be based on those 4 known series. So I highly encourage you to pause the video, try this question on your own, and then play it again to see what we got. Okay, so for number 10, I notice a couple things here. First of all, I noticed that the first thing I'm really always going to look at are my factorials. Factorials are going to be a really big help as far as leading you to what series we're working with. So I noticed that my factorials go essentially 0 factorial, 1 factorial, and then 2 factorial, 3 factorial. It looks like that's what it's doing. And so I think about the series that I know about, and there's really only one series that I know that has a factorial pattern like that. Like I said, factorial pattern is going to be pretty key. So the function that I know about that has a pattern like that is e to the x. E to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot, dot, dot. And so now I've got to look and try to decide what has been done, because you know the factorials here do match e to the x, but the x's definitely do not. So again, if you haven't paused the video and tried this on your own, just I think listening to me talk about it, watching me do it, probably not going to be quite enough. Put some of your own energy into this and see what you come up with. If you can't, of course, watch the video and you should be fine. But see if you can figure this out on your own. What's happened here? Okay, so I noticed some key features here. I noticed, of course, the 1 didn't change, but the x became negative x squared, right? And then, of course, my x squared became x to the 4th, and then my x to the 3rd became negative x to the 6th. We developed an alternating pattern in here, didn't we? So with this alternating pattern, notice how all of the even number terms, like the 2nd and the 4th, or excuse me, all of the odd number terms, I guess would be the 1st and the 3rd, are negative, and then the even number terms, like the 0th and the 2nd, those are positive. So bottom line, here's what I think we've got. Let me try to construct this. If I replace the x with negative x squared, I think what I'm looking at then is 1 plus negative x squared. I'm just going to replace all my x's with negative x squareds, plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial plus dot, dot, dot. I think we'll find that this works out great. When we try to simplify a little bit, we know that negative x squared squared would just be plus x to the 4th over 2 factorial, and then similarly with that 4th term, it would be minus x to the 6th over 3 factorial. And so we can see then, of course, that this matches that. And so I'd say that the series that we were originally presented with is representing the function e to the negative x squared. Okay, let's take a look at number 11. Number 11 says use a known series to determine the function represented by that series right there. So again, we're looking for the function that is represented here. And I think your best bet is to start off by looking at your factorial pattern. What do you see? Well, hopefully you notice that the factorials are all odd, right? 1 factorial, 3 factorial, 5 factorial, 7 factorial, they're all odd. So of all the known series that we are aware of, which is the one that has all odd factorials for denominators? Well, of course, that's sine. So let's remember, sine of x can be represented by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 right? So now let's compare. Let me move this a little bit there. There we go. Let's compare here. So if I look at the first term, my first term in my known series is x. This one is 1. My second term should be x cubed, but it's x squared. The third term should be x to the fifth, but it's x to the fourth. Are you noticing that with each of these terms, there is an x that's been divided out, right? It's been removed. And so I think that's our key. If I divide everything through by x, so sine of x over x equals x over x minus x to the third over x times 3 factorial plus x to the fifth over x times 5 factorial minus x to the seventh over x times 7 factorial. I think you see that the x's will cancel on each term. We end up with 1 minus x squared over 3 factorial plus x to the fourth over 5 factorial minus x to the sixth over 7 factorial. And you can see that it matches. This matches with this. And so this series that we were originally given is representing sine of x over x. So this would be your answer right here, sine of x over x.